Hello there, my name is Gary Sims and this is Gary Explains. Now in this video I want to talk about virtual memory. It's one of the building blocks of modern computing. You find it in your desktop, whether that's Windows, Mac OS, Linux, they all use virtual memory. Laptops the same, tablets the same. In your phone, whether it's an iPhone or an Android phone, they're both using virtual memory. In fact, even the servers that Google are using to stream you this video are using virtual memory. It's almost everywhere. So if you want to find out more, please let me explain. Okay, so when we're talking about virtual memory, we're making the distinction between a digital representation of something and the real world memory or the physical memory. So every laptop, every PC, every server, every smartphone has actual physical RAM, random access memory, and that is mapped or represented inside the operating system using virtual memory. So virtual memory helps modern OSs divide up the physical RAM so that each process, each task, each app that's running has its own address space. So that brings us on to the idea of virtual addresses rather than physical addresses. The actual RAM itself, each location in the RAM has a physical address, but inside the operating system we have these virtual addresses. Now each process has its own address space and it can theoretically only access memory that it owns. I say theoretically, of course, because there are security problems, but that's a whole different subject for a whole different day. So process 101 might have address 1, 2, 3, 4, 5, 6. Maybe it's a game, it's keeping the score in that memory location. Now you may have a task running in the background, let's say checking your emails, and it's using, let's say, something to do with the networking. It's keeping a number related to the network protocols in there. Now they both have address 1, 2, 3, 4, 5, 6, but they're both being used for completely different things. And in fact, each is a different location in the physical memory. So the virtual addresses can be the same, but they map to different physical addresses. And to do that, we use a thing called pages. Now the virtual memory and the physical memory are divided up into equal sections called pages. So the size of a page in the virtual memory has to be the same the size of a page in the physical memory. And typically they are 4K in length. Of course, 4K is a nice number, a nice power of 2 number, 4096, and we'll look a bit more about that shortly. Now pages in virtual memory are mapped to what's called page frames in physical memory. Sometimes people just say pages and pages, frames sometimes, but you have to make the distinction between what's in the virtual memory and what's in the physical memory. So pages are in virtual memory, page frames are in physical memory. So here I've got now a little diagram of a virtual address space. It's only 64K. Of course, it's very different to what's really going on. You're talking megabytes, gigabytes in your actual kind of PCs. But here we can see that everything from 0 right up to 64K is the virtual address space. Now each of these pages, as you can see, these are 4K each. Look, 60 to 64K, 56, 60K and so on. Each of these are mapped to a place in physical memory. Now in physical memory here we're just showing we've only got 32K. So the first thing is we can have a virtual address bigger than the physical address, because when they're not used, there's just no mapping. And of course, a program may not use all of the virtual address space, especially if the virtual address space is 4 gigabytes or even bigger than that. It's not going to use it all. And when it is used, it's mapped over. So here it's mapped to section 6, and that is this section here, the 6th one, the 6th page in the physical memory. We can see down here at 0 that it's actually mapped over, follow the arrow to number 2. So 0, 1, 2. So it's in there. So when an address is actually accessed in the range 0 to 4096, it's really going to be in the range of 8 to 12K in the physical memory. So we're assuming 1024 bytes per K and 4K pages. Page frame 0 is from 0 to 4095. Page frame 1 is from 4096 to 8192 and so on. So if a program tries to access the address 3101, that's a virtual address, and it's down here in page 0, so it's less than 4096. Okay, what happens is it looks at the mapping that follows it through to here, and actually it will be an address somewhere in this page frame 2, which is in the 8K to 12K. And in fact, actually works out its address 1123. Now, how do we go from 3103 to 11293? These are all decimal numbers. Well, we're going to look at that in a moment. Now, before we look at that, we need to understand that this is not something that's done in software. This is something that's done in hardware each CPU, each processor has a memory management unit, and the memory management unit is responsible for doing these translations of these virtual addresses to the physical addresses in the hardware on the fly. So modern processors have a dedicated piece of hardware that handles the mapping between the virtual memory and the physical memory. And the way it works is the MMU holds a table, just like the one we saw in that previous page, that maps the pages to the page frames. So the MMU is pre-programmed. You say, hey, I'm just creating a new task here. These are the bits of memory it's going to be using. Here's how you map from the virtual memory to the physical memory. And then when the task starts running, the MMU can do that translation on the fly. And this is how we might represent the page table, and we're going to see how we translate from the virtual address through to the physical address. Remember, 3103, 11293. So this is the page table, exactly the same page table as I showed you a couple of slides ago. Look here, page 0 maps through to page frame 0010, that's 2. Page 1 maps through to 1, page 2 maps through to page 5, and all the blank ones here with the 0 show they're not mapped at all. And we'll talk about why that's important, having this flag for what's mapped and not mapped in a moment. But you can see that the page table has some mappings over to the physical RAM. So what happens is when you take the virtual address here, we look at the first 4 digits. Well, in fact, they are 0000. So we know that it's in page 0, and you take that and you look it up in this table here. Oh, where is it? Well, it's here, of course. Okay, so that gives you a lookup point in this table. And then the corresponding side of the table is 0010, which we saw was page 2. That gets automatically copied over here now into the physical address. So rather than this first part being 0000, it's now 0010, and it got that number from the page table. And then the great thing is the rest of the address you just copy over. And so it actually turns out that the difference between 3101 and 1293 is nothing more than the fact that this 1 has been switched here from a 0 to a 1, because it's no longer 0000, it's 0010, it's in page 2, and that's it. Everything else remains the same, and you've now got this address. Now obviously for a computer to copy bits from here to here is pretty quick. To look up something in a table is not so bad, and then it can very quickly generate that physical address based on this virtual address. Now a different task would have a different page table, and this first part would map to somewhere else, but this second part would always be the same because it's called the offset. So it's the page and the offset. Now earlier on we saw that there were some pages that were marked if they were present. There is a flag to mark if a page has a corresponding page frame. If the program tries to access an unmapped virtual address, then the CPU, the MMU, raises a page fault. And you may have heard that term, page fault. So what is a page fault? Well, there are 3 different types of page fault. A hard page fault is where a page frame is not in memory, but it is out on the swap space. So at this point, the OS needs to say, all right, I better go and fetch that back from the hard drive, from the flash memory, from wherever, and actually I'll put it back into memory, modify the page table, and then the process can carry on. So a hard page fault is when there is the page is available, but it's actually out on swaps. It's not actually in memory. Now, a soft page fault is if the page is actually in memory but not marked in the MMU as being in memory. So it is there, but the MMU doesn't know about it. Not that it's actually on disk, it's actually in memory. And this is called a soft or a minor page fault. And in this case, then the MMU will just be reprogrammed by the OS to make sure that the actual page can be found. Now, why might this happen? Well, for example, if you have read-only shared memory, so a library that's been loaded up, actually it's already there in memory. You don't need to actually go and load anything. You just need to tell the MMU, hey, actually the library you're looking for is mapped over here at these addresses over here. So that's a soft page fault. Now if the program tries to access an address that is not mapped at all and it shouldn't access it, then that's when you get a segmentation fault or an access violation. And for example, this can happen if the program tries to write to read-only memory. So if it tries to write to itself, for example, write over the code, then you will get an invalid page fault. If you try to dereference a null pointer, if you get buffer overflows, all these kind of cases, basically the MMU says, no, I'm sorry, I can't deal with that address, and it raises an invalid page fault or an access violation. Now, there are some problems with this little scheme that I've just described, because we were dealing there with 64K. And that's not a problem, but of course modern day computers, we're talking about 32 bits and 64 bits, 8 gigabytes is 8388608K, which means if you divide that into 4K entries, you need 2 million pages. So you need 2 million pages in your MMU. Well, that's an awful lot of space, and that's just for one process. Okay, and so if you then get another process and another process, in fact, if you just go down to 32 bits just to make it kind of the numbers a bit more manageable, you would need 4 megabytes of table for a full 32-bit program. And then if you've got 100 tasks running, well, you need 400 megabytes and you need half a gigabyte of RAM just to hold the tables. You're not even running the programs at this point. You haven't even got any of the graphics or sound or media loaded up. You're just running the programs and you need 400 megabytes of tables. So obviously this is not a good idea to have all of these tables. And the point is that it needs to be fast. And if you've got to search through 400 megabytes of tables for every single address that you load up, whatever solution we come up with, it needs to be blisteringly fast. And the other thing is that 400 megabytes can never leave the RAM, because they're always needed for any address lookup. You need to have it, so you can't do anything other than have them in RAM. And of course, 400 megabytes, more if you're starting dealing with 64-bit, you're starting dealing with bigger programs, you're just taking up RAM that you don't necessarily need. Why? Well, one reason, of course, there are gaps in that memory. You're not going to use all 32-bit address space or all 64-bit address space. You're not going to use 4 gigabytes of physical RAM. So your virtual has got gaps in it. So where between the stack and the data and the program, there are going to be big gaps, sometimes even 1-2 gigabytes of gaps, and you don't need all those page tables. They can be ignored. You don't need them, but yet, using the method I just described, you need an entry in each one at least to say it's invalid, it's not mapped. So there is another level of a deeper, complex solution which uses the same idea, and that's basically multi-level page tables. So rather than just one big table, you have a hierarchy of one table underneath another, and we'll look at that now. So here is a few entries from our page table, and you can see we've got page 000, 001, 0010, 0011, 0100. Now the point you can note here is that these first 2 bits here are always 00. And then when you get into a second section here, they're always 01. So memory, by the nature of binary, of course, you can already draw a line across this middle bit here and say, hey, these are two different kind of segments here. The address is starting with 01 and address is starting with 00. So you can actually divide this table into 2. In fact, if we show a little 3 divider here, 00, 01, 10, 11, you just keep going on and on and on. And rather than actually the address lookup as we were showing with the page number and the offset, you actually say, no, there's another place in memory which has got more information for you. So the only thing now that needs to stay in memory is this table. And this table has far less entries in it. And the rest of the tables, which are here in actual memory, can be swapped out. They can be swapped out to disk, or they may not even be there, but you don't need them if you don't use them. So now as a way of actually, like this one here says, not present, well, all we've got is one entry, but now a whole bunch of stuff in this table is not there, and it's not using any of our physical memory to hold something we don't need. As long as we've got this top level table in RAM, the rest of the tables can either not be there or they can be swapped out. And of course, that's a brilliant advantage in both of efficiency and of course in being able to use the swap space. So if we do divide that into 2 tables, we can see you've got 01, 01, 01, 01, and then all the rest of it, and 00, 00, and then the same thing's the same. Look, this was an address AB14, AB18, exactly what was shown here in our top level table. And basically then it's the same thing, you just do the lookup. So 0011 gives you page frame 0000, and then the offset is copied over and everything is exactly as it was before. Now here is a page from the RISC-V manual, and this is for 48-bit virtual addressing. And as you can see here, it's using 4 loads of virtual tables of nested multi-level tables, a 4-level page table. So each one of these is a reference to the next level of table, and then that gets translated through to a physical address. Now the interesting thing is here is the physical address is actually longer. So when you start doing these multi-level things, you can actually start to create some interesting ways of performing the mapping. So notice here it's 9 bytes, 9 bits, 9 bits, 9 bits, 17 bits on that last one. And in the page table, that's what this last one here, you can see that last one there is 17 bits. So you can actually end up with a bigger physical addresses than you have with the virtual addresses. Now, the key thing to note about this is these flags down here. This is a real detail for you. That V flag means whether it's valid, whether it's present or not, basically. So it can raise a page fault if it's not valid. And these three here are the permission bits. X, X for execute, W for write, R for read. Okay, it tells you whether the code can be executed in that page, whether you can write to it, and so on. Now, if all of them are 0, if all three are zeros, then the page table entry, PTE, is a pointer to the next level of page table. So instead of it being these little lookups, it's actually the rest of this. Here is the address where you'll find the next level of page table. So very quickly, the MMU can look at this and say, right, this is a pointer to the next bit. Okay, now I'll jump down to the next level until finally you get a leaf, the final end of your chain of tables, and that one has the actual lookup in it, as we've been discussing until now. Now, to access a virtual address, the CPU, the MMU, needs to access several other addresses in memory. So to access one address, you might need to access 4 other addresses in the memory. So that might seem slow. Basically you're slowing everything down by a factor of 4, because every time you want to create a virtual address, translate a virtual address through to a physical address, you've got to access 4 other physical addresses, follow all that tables, fish out the page numbers, and then copy over the offset. Now, this is slow, and it also seems paradoxical, doesn't it, that you have to access memory to find out what an address is. So there is a way around this that speeds this up significantly, and that is something called the TLB, the Translation Look-Aside Buffer, or the Translation Look-Aside Buffers. The TLB is a cache of the recently accessed page translations in the MMU. So for each memory access performed by the processor, the MMU checks whether the translation is already cached. And of course, if you've just been accessing something inside of a 4K page, then you move on to the next address where you've already got that translation. All you're doing is changing the offset. So especially when you're dealing inside a small section of 4K code, you're actually going to have that already in the cache. If the requested address translation causes a hit within the TLB, the translation is immediately available. Now, every TLB entry typically contains not only the physical and virtual addresses, but also some attributes like the memory type, caching policies, access permissions. So in itself is like a cached version of the page table. If the TLB does not contain a valid translation for the virtual address, then that's a TLB miss, and then the actual external walking has to happen. But remember, once you're in a page, actually inside a 4K page, you don't need to do it again because you're just changing the offset. So this miss doesn't happen every single time. It's actually every time you change a page. And if you've got enough entries, you can keep quite a cache of pages available. In fact, if we look here at the ARM Cortex-X1, you've seen some of my videos about this. You may have noticed this block called the TLB, and now you've wondered what it was. Well, now you know, or maybe you already know, but there it is. It's the level 2 TLB. So it's actually there inside of the processor, level 2 access cache, and it allows the processor to have access to those translations. And if you look over here, one of the ways they improved the performance of the X1 was to offer a larger TLB. It's now got 2,000 entries in it, and that's 2,000 entries, of course, for every 4K page. So trying to increase the number of times you get a cache hit in the MMU, so you don't have to go and travel all those tables to get you the next address translation. Okay, so there it is, my quick look at virtual memory. I really hope you enjoyed this video. If you did, please do give it a thumbs up. And if you like these kind of videos, why not stick around by subscribing? Also, don't forget you can follow me on Twitter at Gary Explains, and I also have a monthly newsletter. Go to garyexplains.com, type in your email address, no spam, but you will get the email. Okay, that's it. I'll see you in the next one.